Hi, and today is derivatives day 5, and today's topic is derivatives of exponential functions. So before we get started, let's just do a quick recap. So if you guys remember, I already mentioned the differentiation rules for the power functions, and I told you guys to be careful between the power functions and the exponential functions, and today I'm just going to remind you of that and talk more about exponential functions. So this is basically the differentiation rules for the exponential functions, i.e. the ones that I told you not to do to use earlier for the power functions. So let's just do a quick definition so you guys can remember. So power functions, we said the difference between them is that a power function is when there is a variable in the base and a number in the exponents section. So a variable in the base and there is a number in the exponents, right? That is pretty much what defines a power function. An exponential function, we said, was the opposite. It's where there is a number in the base and a variable in the exponents section. And so when we were looking at rules for power functions, I was telling you guys to be careful to not mix power functions and exponential functions by accident, because then they do not have the same rules, the same differentiation rules. So you would result in a wrong answer. So today I'm actually going to be talking about exponential functions. So let's get started. All right. So before that, let me just talk about something called. Sorry if I can't pronounce his name, but Euler's numbers, EULER apostrophe S numbers. Basically, you're going to be seeing this a lot in calculus 12, and it's the symbol E, and basically it is the base that yields the slope of the line tangent to the curve y is equal to a to the power of x at x is equal to 0 to be 1. All right, so basically this number right here, which is approximately 2.7182818228, this number right here, basically it is the slope of the tangent line for the graph y is equal to a to the power of x um, at x is equal to 0. That would give you a slope of 1. All right, so this value, if this value was plugged into here, right, and the slope rate there at x is equal to 0 would be exactly 1. So while at first this might not be helpful or obvious, because this again differentiation deals with slopes of tangent lines and instantaneous rates of change, this will be important later on. So I just wanted to mention this. Basically, the way you can write it usually in calculus is in the exponential form, which is e to the power of x. And e itself, again, is roughly approximately 2.7182818828. You don't need to memorize that value. It's actually already in most calculators. But I just wanted to share that with you as well. So anyway, let's continue on with this. All right, so all you guys need to know, I guess, for this video is just two main values. It's similar to the trigonometric values. You just need to memorize these. They're very straightforward, and this one's super easy. So the derivative of the natural exponential function. The derivative of e to the power of x is literally just e to the power of x. It's the only condition in derivatives, the only rule, the only, I guess, exception where the derivative is the exact same as a function, the original function, so they don't change. This is the only exception. And the reason for that is, again, it has to do with the fact that this will result in a slope of a tangent line exactly equal to 1. And again, if you want more of that, you can check out my website, explain in full detail. I'm not going to go too in-depth in this video because you don't need to know all that for high school calculus. But I just want you to know that the derivative of e to the power of x is just e to the power of x. Super simple, super easy. And that's basically it for the first one. And now let's move on. So now let's talk about the derivative of a general exponential function. So general meaning like any number. So e was only, this condition was only for e. a here, I guess, represents any number except for e. So what if, for example, it was what if, for example, it was 5 to the power of x? How would we find the derivative of that? Right, so the general formula to remember here is that the derivative of a to the x is equal to a to the x ln a. All right, now I'm going to explain that a bit further. So essentially what happens is that when you take the derivative of just any exponential function, it just results in the same exponential function being written here, and then you take the ln of the base. Ln is just the natural log. So if you guys can remember, there are logs and logs have bases. So the natural log is basically just a log with a base e. It's written as ln, and this is the same e that we just talked about earlier. So that's just what I'm trying to say, that Euler's number, I'm not sure if I said it right, but it has, also known as the natural exponent, it plays a huge factor in calculus, and also its log form as well. So ln is equal to log base e. So that's the formula. Basically, the derivative of any general exponential function will result in the exponential function itself being multiplied by the ln of the base of that function. So here we have two different examples, and they actually relate to a couple of our topics that we learned. So for A, we have y is equal to e to 3 minus 4x. You can, I'm not sure if you noticed, but e to the power of 3 minus 4x, that is actually a composite function. Again, if you don't know what that is, please check out Derivatives Day 4, where I talk about chain rules. So that is definitely a chain rule, and the chain rule definitely applies. For the second one, we see f of x is equal to 3 to the power of cosine x. There's definitely a chain rule, and you also have some of your trigonometric rules for differentiation kicking in as well. So let's start off by answering A, y. Let me just write A so it's clear. A, y is equal to e to the power of 3 minus 4x. E to the power of 3 minus 4x, all right? So the first thing you want to do, we want to identify that we are taking the derivative of this, so y prime, or you can write f prime of x, or any other notation you like, as long as it's applicable. And if you guys want to learn more about notations, you can just check out day 1, part 1 of derivatives. So anyway, let's just go back into here. First of all, this e to 3 minus 4x, this stays the same because we just said e to the power of x is equal to 3 to the power of x. So this stays the same. And let me just put that in brackets. And then we have a chain rule going on here for this part now. So the derivative of 3 is just 0. And then the derivative of negative 4x is just negative 4. Right? And I think at this stage we should know why that happens. So all we have here, if we just simplify, is literally e to the power of 3 minus 4x times negative 4, and we can just clean that all up. Negative 4e 3 minus 4x. And that is it. That is our answer. So let me just put that in a box. So that is the answer to A. Again, very simple, very straightforward. It's nothing really too complicated. I actually find it one of the easier topics in this introduction to derivatives unit. Basically, e to the power of x just stays e to the power of x, and then you can just use chain rule where applicable. All right, so now let's go back to, let's focus now on B. So f of x is equal to 3 cos x. All right, B, f of x is equal to 3 to the power of cos x. All right. So let's start off by writing down the formula that we just learned. D over dx of a to the power of x is equal to the a to the power of x, and then ln a. All right. So now what we're going to do is let us now write f prime of x. And then a to the power of x, we have just established that. That is 3 to the power of cos x. All right? and we're going to write ln, and then again a, so, but just the base, not the exponent, and the base is 3, right? So I'm just going to write base is 3. All right, so ln 3, and now you got to pay a lot of attention here, because most people might just jump to conclusions and say they're done, but we're actually not, because if you guys can remember, there's chain rule. This is a function inside a function. Cos x follows special differentiation rules, so we need to remember to differentiate that as well. So I'm just going to set up a multiplication here, because when you have chain rule, use multiplication to basically pretty much separate the different differentiations. So what is the derivative of cosine x? If you guys can remember from day 3 of trigonometric differentiation rules, that'll be negative sine x. All right, so the full answer is, I'm just going to write that again, cos x ln 3, I'll put that all in brackets, negative sine x, and there we go. So just, and this is fine, there's no, you don't need to simplify this any further, and I don't think it can be. I know it kind of looks long, but it's the answer, and it's totally allowed. But again, just please remember, the chain rule is very important. You got to always be on the lookout to make sure that whether there is chain rule or not, so whether you potentially have a function inside a function. Anyway, that's it for today's video. I think today was actually not very hard, super easy. Again, I just want to remind you guys, please check out my website, link in the description. I have full explanations, extra notes, extra practice problems with varying levels of difficulty, easy, intermediate, and hard. And I also have solutions to all those problems with all the work shown, so you guys can understand how I got my answers. Also, if you have any questions, comments, or concerns, please email me at helpwithmath0@gmail.com. That will also be in the description. And other than that, that's it for today's video. Thank you guys so much for tuning in.